Today's topic is significant figures. What is accuracy? It's your measurements, how close they are to the true value, how close they are to where you want those measurements to be. However, precision is how close your measurements are to each other. So you're taking several measurements, and how close are those measurements to each other? So here's an example of accuracy and precision in terms of taking shots at a target. So in this illustration here, the shots are all over the place. This would be an example of low accuracy and low precision. In this situation here, we're very, very close. We're very accurate to the true value. That's where we want to hit, but our shots are not grouped together very well. So this is an example of high accuracy, but low precision. Here's the opposite. Our shots are very, very close to each other, but they're not hitting the target. This is an example of low accuracy and high precision. And then finally, what we're shooting for, literally, is we want our measurements to have high accuracy and high precision. In this situation here, if we think about targets and maybe you're shooting a bow or something like that, this is probably from maybe a very unskilled shot of the person. They don't know what they're doing, or maybe the bow is not very good. In this situation here, it's probably a really good bow, but the person's not an expert. So the bow's really focused on there, but they're just not holding their hand very well. So when you have high accuracy and low precision, this is usually operator error. This is usually because the person's making a mistake. On this situation here, this is very precise. The person is really dead on. This is probably a problem with the device. So perhaps the scope on the bow is off. So they're really holding it straight and they're shooting exactly where they want to, but it's grouping over here. So when you have high accuracy and low precision, this is usually operator error. But when you have low accuracy and high precision, this is usually an error with the calibration of the equipment. When everything goes right, this is the situation we get. So let's talk about significant figures. Let's talk about numbers. You might have learned in math that 25.00 is the same as 25.0, which is also the same as 25. In science, there is a difference. It's a big difference between 25.00 and 25.0. So let me get into this. The reason these are different is because they're different types of measurements measured with different types of equipment. Even though I don't have a picture when I see this number, I know something about the equipment that was allowing me to measure to the 100th of a milliliter. But in this measurement, I was only able to measure to the 10th of a millimeter. And so let's take a look at what this might look like when we're taking these measurements. If I have a measurement here, the water is lined up exactly at the 25 milliliter mark. But if you look here, between these marks between 24 and 25, these are tenths. So this would be 24.1, 24.2, 24.5, all the way up to 24.9, and this is 25.0, 25.00. In between, we could also make a measurement. So it's possible, like if it was right here instead, that would be 24.9, and it's halfway there. So that would be 24.95. So 24.95, see, I would have 4 significant figures there. Just because it lands on the 25, I don't negate those zeros. This is telling me what type of equipment I'm using. However, if we go to the other side here, this is 15 milliliters, this is 25 milliliters. So every one of these increments is a milliliter. So this is 16 milliliters, 17, 18, 19, 20, 21, 22, 23, 24, 25. And if I was in between this mark, that would be 24 milliliters. But if it was halfway between there, that would be 24.5. So measuring in between these lines here, we get it to the tenths place. And again, just because it lines up right on a line, we do not remove that zero. Point being, when we take measurements, the last number is always an estimate. Like I was saying over here, this could be 24.95, but it's kind of hard when you actually look at it in real life. It could be a little below. Somebody might see it as 24.94, somebody might see it as 24.95, and both are actually okay. This last number is an estimate. If I didn't put these zeros, that would mean the 5 was an estimate. That would mean you didn't have a very precise measuring instrument. So, how do we count significant figures? When I give you a number, how do you know how many significant figures are in that number? And there's some rules on that. The first rule is rather easy. If it's a non-zero integer, that means 1, 2, 3, 4, 5, 6, 7, 8, 9, they always count as significant figures. For instance, the number 2 has one significant figure. It's one integer. 27 has two significant figures. The two significant figures are the 2 and the 7. Decimal places do not change anything with significant figures. There are still 3 integers. So this is 3 significant figures, a 2, a 7, and a 1. You do not count a decimal place as a significant figure, and it doesn't take away from the fact that there is a number over here. So this is 3 significant figures, so 27.1. So if it's a non-zero, it counts as a significant figure. Zeros, on the other hand, give us some problems. There are 3 types of zeros. The first type I want to talk about is a leading zero. Leading zeros precede the non-zero digits. They do not count as significant figures. They're only placeholders. So if you have leading zeros, see, this is when I start to have non-zeros. These zeros are in front. These are called leading zeros. These are not significant. So 0.0025 has only 2 significant figures. They're just placeholders. So all 3 zeros simply indicate the position of the decimal place. The number only has 2 significant figures. The next type of zero is a captive zero. Captive zeros are zeros that go in between the non-zero integers, such as this number here, 2,600,002. So we have the 2, the 6, and then we've got another 2 here, and we've got 4 captive zeros. Captive zeros are in between, and they always count. So 2, 6, 0, 0, 0, 0, 2. So that's 1, 2, 3, 4, 5, 6, 7. There's 7 significant figures here. 1.008. These zeros are captive. Don't let the decimal place trip you up here. So how many significant figures are in this number? There would be 1, 2, 3, 4. Now, the last category of zero is a trailing zero. Remember, leading zeros never count. Captive zeros always count. Trailing zeros sometimes count. And this does confuse people, but pay attention, take some good notes, and it's not that bad, but I think some people don't think about this very much and they get confused. So, trailing zeros are the zeros to the right of a non-zero integer. So here we have 2 trailing zeros. They only count, so they sometimes count, they only count, they are significant only if the number contains a decimal place. So in this number 100, there's no decimal place, and therefore it has only one significant figure. These zeros are only placeholders, just like the leading zeros that were placeholders for the decimal place. Trailing zeros can be placeholders as well. So this one only has one significant figure. This is, by the way, the number 100 written 3 times with different amounts of significant figures. In this situation, the number 100 is written in scientific notation, which we'll talk about more later. So 1.0, because there's a decimal place, it contains a decimal point, that means this trailing zero counts. See, there's no decimal point in this number, therefore these trailing zeros don't count. Because there's a decimal place, this zero does count. So there is 2 significant figures when you write 100 in scientific notation. Please note, when we talk about scientific notation again later, that the 10 to the second, this here does not count as significant figures. These are just placeholders on extra zeros. This just means you move the 0 over twice. or the decimal place over twice. In this situation here, the number 100 written again with a decimal place, there are 3 significant figures because there's a decimal place, so it counts those zeros. Just because you have zeros doesn't make it a significant figure. So that's why we have these exponents. In other words, if you're confused on why don't the zeros count, like the number a million, which instead of these zeros are not significant, we can say mega. So we might say like it's 1.2 megagrams. That would be 2 significant figures. It's a large mass, but we didn't measure something very, very precise towards the end. We can also look at things that are small. By the way, you should be familiar with the metric system up to giga in this class. So deca, hecto, kilo, mega, and giga. You should be familiar with these large numbers. That's just adding zeros. And again, adding zeros doesn't make it significant. And then we could also go on the opposite side of that and take a look at making it a very small number. So these prefixes you should be familiar with too: deci, centi, milli, micro, and nano. And in this situation here, it's just getting a smaller number. So when we talk about nanograms or nanometers, we're talking about maybe the size of atoms or the distance between atoms to each other, or bonds and stuff like that. These zeros are not significant. They're just placeholders to talk about a very small number. So we can say 9 nanograms or something like that. By the way, a micro is a special character. It's called a mu. It looks like a U and it's got a tail in front of it. So it's not a typo. Your eyes aren't deceiving. So when we're looking at prefixes, we're looking at adding prefixes doesn't make a number more significant. It just talks about maybe making a number larger, or we could talk about making a number smaller. But all these zeros are not significant. Again, there's a decimal place here, but these are leading zeros. If we have zeros behind these ones, then that does become significant because those are trailing zeros. So keep in mind the different types of zeros we're talking about. Another thing I'd like to talk about is when we're counting, that does not count as significant figures. It's not a measurement. These are exact numbers. So some other examples of exact numbers is that 1 inch is exactly 2.54 centimeters. This will make more sense the next lesson I'm going to talk about, because we're going to do calculations with significant figures. But this 1 inch and 2.54 centimeters, there's no limit to the significant figures here. In other words, this is not 1 significant figure. This is not 3. If it's an exact number, it doesn't limit the amount of significant figures when we're doing calculations. So remember that, because next time we will be doing calculations. But right now, I just want you to identify significant figures. When we're counting, there's 3 apples. There's no limit to your significant figures there, because you think about that. Significant figures are, can we measure this a little bit better? Can we get another decimal place in there? Can we get another, unit in there? Not unit. Can we get another value in there, another integer? So the better your equipment, the more significant figures you can record. But you can't say there's 3 apples. Can you go back and count that better? I want more significant figures. There's just 3 apples. So these are examples of things that would not limit you in significant figures with your calculations. So let's go here. We got this number 1,274.52 cents. Now, sometimes when you're purchasing things, if that's how much it costs, and somebody, maybe it's a new phone or something like that, and it's really nice, and that's how much you paid, and someone's like, well, how much is that phone? You might just say the phone, it's $1,000. Now, everyone knows you're not going to go to the store, and it's not going to be $1,000.00. It's about $1,000 is what that phone is. You answered with 1 significant figure. These zeros are not significant. You are giving a imprecise number. The more significant figures, the more precise the value. So like if you say how much was the phone and you said $1,274.52, people will be like, wow, I don't need that much information. You gave an answer with a lot of significant figures in it. So sometimes we round off. When we round off, the number becomes less precise. I hope that makes sense. So let's take a look at this number now with 2 significant figures. if your calculator comes up with this number, but you need to record it with two significant figures, you would take the first two numbers, and if the third number is 5 or greater, you would round up. So if it cost you $1,274.52, you might say this phone is about $1,300, and that makes sense. It's closer to $1,300 than it is $1,200. Let's do this with three significant figures. Again, you take a look at the first three, and if this is a 5 or greater, you round up. It is not, so we would record this as $1,270. Four significant figures, that means we're going to go right up to this point here. And because after this 4, we have a 5, it rounds the 4 up. So with four significant figures, we'd say 1,275. And I could hear somebody saying something like that with it. If we were going to do this in 6 significant figures, I would stop at this point here. And remember, there's a decimal place here. So if I added another 0, that would make it significant because there's a decimal place. So I have to leave that off. With 6 significant figures, that's exactly what it is. 1,274.52. Now, what if your calculator came up with this answer, but you're supposed to record the answer with 7 significant figures, where your calculator only gave 6? Well, you know what you would do? You would add a 0. You would add a 0 to it, and now there's 1, 2, 3, 4, 5, 6, 7, and because there's a decimal place, that 0 is significant. So you could write this number with 7 significant figures by adding a 0. Remember, if there's a decimal place, trailing zeros count. Now, let's talk about measurements and where do we get these significant figures in the first place? Because in lab, we're going to be taking measurements and we got to figure out how we're going to record these things. So if you're using a ruler, the millimeter marks are so small, you can't really estimate between the two. So it is appropriate when you're using a ruler that has millimeter marks. These are centimeters right here, and the little ones here are millimeters. It is appropriate to measure it to the 1/10 of a centimeter, which is a millimeter. So in this one here, you can see that it's 5. It's not quite to 6, and it's above the halfway point, so that would be 5.5. It's right here to that 5.6. So 5.6 centimeters would be the way you would read this ruler. It's very important you measure and record the proper significant figures with the different instruments you get. So if it was right here on the 5, you would need to record it as 5.0 centimeters. Very important, guys. This is an example of reading a triple beam. In a triple beam, you've got 3 different masses. The two of them go into slots. It's either going to be 100, 200, 300, 400, and then the other one above it goes by tens only. And then you've got a slide that goes back and forth. So if we're taking a look at a triple beam, what you do is you add up the numbers. So we've got 200 plus 40, and then here would be 241, 242, so it's 241, and this would be 241.5, 241.6, and then this would be 241.5, 241.6, this would be 241.7. It's not to the 7 yet, it's to the 6, and it's not quite halfway there. Somebody might read this as 241.62. Somebody might see it's a little bit more to the right, 241.63. Somebody might see this more to the left, 241.61. You might even see it higher, 241.64. In fact, I'm seeing it higher right now as I'm looking at it. I might even say 241.65 or even 66. Point being is this last number is an estimate, and those are all acceptable answers. When you're reading fluids, like water, is a polar molecule, and it attracts to the glass, which is also a polar molecule, silicon oxide. And because it attracts the glass, it makes a little curve in a very narrow situation, like a graduated cylinder or a test tube. It gets this curve, and this curve is called a meniscus. When you're reading it, you have to have eye level right where that meniscus is, so you have to get right down low on it. If you look at it from an angle, you will read the wrong value. So that's really, really important. If you're using a fluid that is nonpolar, then it will repel from the glass, and the meniscus could curve the other direction. So you can get a meniscus that curves in different types of directions. But when you're reading it, you're reading the peak or the valley of the meniscus. So here's the lowest point, and here's the highest point. That's how you read fluids. So if we take a look at this, again, when you're reading something, you have to figure out what those units are. So here is 10 milliliters, and this would be 25, this would be 26, and it's not quite to the 26, it's in between the 26 and the 27, so I'm recording this as 26.50. In this situation here, I've got 30, 31, 32, and the meniscus is right at the 32, but I'm not going to record this as 32 evenly. That would mean I estimated this too, so that's why I'm putting the 0 there, 32.0. So again, make sure that you're using the proper significant figures when you take these measurements. Where can you estimate? You're estimating between these lines, so therefore that is the last digit you're going to be recording. All right, so now we got some checkpoints. You can pause the video and practice these things. If you go to my website, you can download the checkpoints, but I want you to know how many significant figures are in these different values. So here's one. These are just some numbers. Can you identify how many significant figures are in these numbers? You can pause here. The next one is, can you write this number with different amount of significant figures? So write this number with 1, 2, 3, 5, and 7. I skipped the 4 and I skipped the 6. So 1, 2, 3, 5, and 7 significant figures. You can pause here. Next one is take a look at this ruler and write down what these measurements are. And we will be doing a lab on measurements and being able to read things appropriately. So just make sure that you're measuring to the proper level of significant figures. Again, you can pause here. And you can pause here. Read this triple beam balance. What does that number read? And here is a graduated cylinder. What would the value be of this graduated cylinder? If you have any questions, let me know, contact me, and I'd be happy to help you. Good luck, and I'll talk to you soon.